Hi class, welcome to Refrigeration and Air Conditioning, lecture number 10. We'll look at gas cycle refrigeration applications in this lecture. So you have learned about gas cycle refrigeration and reverse Brayton cycle in the previous lecture. Um, and you already know that in gas cycle refrigeration, there is no phase change. It's mainly gases going from a high pressure state to low pressure state, and in some situations they undergo heat transfer. So typically, the um, refrigeration effect involved in such cycles is basically gas expansion. So when the gas expands, it cools, and the cold air removes the cold gas removes the heat from one place and transfers the heat to a warmer place. So there are two primary applications for such cycles. These cycles are not very efficient, so they're only used for special cases. One is aircraft cabin cooling, okay, and the other is cryogenics and liquefaction. If you are familiar with liquid nitrogen, liquid oxygen, etc., they are liquefied at very cold temperatures through the use of gas cycle refrigeration. Now, aircraft cabin cooling primarily uses isentropic expansion. In cryogenics, it uses both isentropic and isenthalpic. The isenthalpic one is the one we have seen in a few lectures ago, and we have studied that it is the Joule-Thomson effect. Okay, so the gas expands through a throttling device and drops in pressure. In isentropic expansion, gas is not only dropping in pressure, but it's doing some work. So it's doing some work in the turbine. So that causes it to further drop in temperature. So the refrigerants used for aircraft cabin cooling is, of course, air. And the refrigerants used for cryogenics are typically helium, hydrogen, nitrogen, and neon. So you could liquefy these gases too using cryogenic techniques. All right. So first thing, let's just compare these two cooling methodologies or the cooling effects, the isentropic versus the isenthalpic. And you should remember that it's not really fully isentropic. It is close to isentropic because it's doing some useful work, but not uh, all the energy is converted to work. Some of the energy gets converted to heat too. So it's not fully isentropic. And you also know that it's happening really fast. The turbine is spinning really fast. So that also means that it's not in equilibrium. Equilibrium processes have to occur really slow. Anyways, so this is an example of an isentropic expansion through a turbine, and isenthalpic ones are basically uh, places where you expand through a constricted area. Here there's work done, and here work done in turbine, and here the work done is zero. Okay, so based on this fact, let's use CoolProp and try to understand if uh, isentropic expansion is better than isenthalpic or vice versa. Which one will cause a bigger temperature change? Open the expansion isentropic versus isenthalpic Excel file. So here we are considering air as the refrigerant, and we have an initial and final pressure, initial temperature and pressure, and we are calculating for two scenarios, one where the enthalpy is constant, the other where the entropy is constant. So we calculate the initial enthalpy and initial entropy for these two conditions. Okay, you can look at the formula here. You will put S as the output variable for entropy and H as the output variable for enthalpy. Then you calculate for the same enthalpy, you calculate the final T, okay, using the same enthalpy here. Calculate the final T and develop this this, this list of temperatures as the pressure goes down. Okay, do the same thing for isentropic. Use the same entropy as the initial entropy, and then calculate a multiple sets of temperatures as the pressure goes down. If you compare them, you could see that the isenthalpic pressure temperature drop for the same pressure change, pressure is on the x-axis, temperature is on the y-axis, is much lower than uh, the isentropic pressure drop. So if you're able to do work while you're expanding, you can drop much more pressure in the during expansion. All right. Now, the aircraft refrigeration cycle is an open cycle. What I mean by that is if you consider a particular volume of refrigerant going through the cycle, it doesn't complete the cycle all the way because cold air is put into the cabinet, and the warm air that comes back is a mixture of outside air and also a little bit of recirculated air. So we cannot really say that it's a full cycle. So it's an open cycle, and this is the simplest open cycle Brayton reverse Brayton cycle. Okay. So there's a turbine, a compressor, heat exchanger. In fact, there will be multiple heat exchangers, and there's a way that the warm air is coming into the compressor. So if you further look into the actual uh, reverse Brayton cycle, you have to account for two more inefficiencies. One is the isentropic compression is not really isentropic, it's non-isentropic. So instead of going straight up here, where the entropy will be constant, you have to move a little bit towards the right. So the process is going along this way, right? Um, so the red line here is the actual reverse Brayton cycle used in aircraft. So in this case, you could see the compression is non-isentropic, then the uh, pressure drop during the heat exchange process, and it's not a constant pressure process, it's actually having a small pressure drop because there are usually pressure losses in pipes and tubes and all that. So that is another inefficiency. And then the expansion in the turbine is not exactly isentropic expansion. So again, you move towards the right. So entropy increases. So entropy increases in compression and expansion because it's a non-isentropic process. And then again, there is pressure drop in the um, cabin, um, all the air that goes through the cabin and then it makes it back to the turbine, sorry, the compressor. There's some pressure drop there too. Okay. All right. Now let's look at a little bit more in detail on the aircraft air conditioning system. It is typically referred to as PAC units. Okay. And the PAC means packaged air conditioning unit kit, or you could also say pneumatic air conditioning kit. If you look at the aircraft, is typically, especially for large aircrafts, is typically under the aircraft, under the fuselage. It's usually behind the engines and near the root of the wings. Okay, and typically most large aircrafts have a minimum of two PAC units. Okay, there will be two such units, and those PAC units have several components. But one thing to note here is the primary air that the PAC units compress comes from the engines. So there's bleed air from the engines that goes to the PAC units, and the PAC units cool that air and exhaust it into the cabinet at the right temperature and pressures. Okay, and some of that air goes back into the PAC unit, and the rest of it is thrown back into the atmosphere. Okay. So what are the components? First is the bleed air source that comes from the engine. So it is a hot air, bypass air that leaves the engine compressor stages, and it then goes to a heat exchanger. It's typically called a pre-cooler. It reduces that high temperature into a low temperature using ram air. Ram air is, if you see, there are some intakes here. It's basically air that is getting rammed into these intake holes, okay? And it's outside air, and outside is usually really cold, -10, -20 degrees C. So the -10 or -20 degrees C air is used to cool the compressed air um, from the turbine to an intermediate temperature. Okay, so you haven't dropped the pressure, you just have high pressure hot air being cooled using the primary heat exchanger to a slightly lower temperature, um, but at higher pressure. Then we have the gas cycle or the gas refrigeration system, which is usually referred to as ACM, air cycle machine. Okay, so it has a compressor and a turbine, and they're attached to each other. Typically, this turbine drives this compressor. Okay, so this is a separate compressor. This is not the compressor on the engine. Okay, so this is basically a secondary compression process. Primary compression is done by the engine compressors, and then there is a turbine and a compressor system together, which is again compressing and expanding. Okay, it also has a secondary heat exchanger, which further cools the air before it enters the turbine. So air from the pre-cooler goes to the centrifugal compressor and then exchanges heat, cools further down, and then expands through the turbine, finally reducing it to the lowest temperature. So the primary and secondary heat exchangers that we talked about here uses ram air because basically it's outside air that is rammed in through intakes on the bottom of the plane to cool compressed air from the ACM. When the air gets cooled in the expansion turbine, the temperature drops so much that there could be moisture forming. So we need a water separator so that all that moisture doesn't go into the compartment. So this removes moisture from the cold air, okay, the condensed water. Um, then we have a mixing chamber that mixes the cold air that comes out of this heat exchanger, sorry, that comes out from the water separator, and um, it is mixed with recirculated cabin air and also the warm bleed air so that you maintain both the temperature and pressure. Finally, the cabin air distribution system uh, puts the air into the compartment and tries to cool the compartment uh, to the required specs to maintain comfortable pressure and temperature conditions under varying ambient conditions in which the airplane is flying. So if you're uh, one of the first doubts you have is why does the airplanes need an air conditioner to begin with? They are flying in upper atmosphere and outside is really cold. So why do we need to further cool the inside of the airplane? Well, the outside is cold, that's true, but inside there are several passengers and each passenger is a heat source, right? So they're confined in there. Plus, you could get sunlight coming through the windows, so there could be additional heating of the aircraft through the sunlight. Um, in addition to that, you cannot um, use outside air to provide, replenish oxygen in the which the people inside are using, because outside is at a much lower pressure. Typically, the outside pressure will be like zero point 0.2 to zero point 0.3 bars, much lower than the atmospheric pressure of 1 bar. So you cannot directly use outside air. And even if you are trying to use outside air, you try to intake it through the ram inlet, it immediately heats up to like 40 degrees C or so because of the speed of the aircraft, and suddenly the air is hitting and stopping. So it rises to its stagnation temperature. So all of that means we need a system um, to cool. It needs an air conditioning system to cool and maintain um, conditions that are conducive for human comfort inside the plane. Now let's look at the pack system a little bit more in detail. So this is an image of the aircraft air conditioning system. Okay, so what are the components here? Um, so basically everything on this side is the pack system that I'm showing here. Okay, this is the engine, the engine of the aircraft, the jet engine. And after the compression stage, you take a little bit of bleed air or bypass air and take it to the first heat exchanger. So first heat exchanger, okay? So the bypass air that is coming in at 165 degrees C and very high pressures um, first goes through this primary heat exchanger. It's pre-cooled. How do you cool it? You take outside air in. And how do you take outside air in? You use ram air inlets. So if you look here, there are some inlets under the aircraft, and that outside air goes in, and that cold air cools the air inside the heat exchanger. So outside air cools this heat exchanger. So it's pre-cooled. Then it goes to a centrifugal compressor. The compressor and turbine are attached to each other. The compressor is driven by the turbine. So the turbine is the one that is spinning the compressor, okay? So as the um, as the compressed pre-cooled air goes through the compressor, its pressure increases again and temperature increases again. And after that happens, we need to go through a secondary heat exchanger again, which is again using ram air to cool it. Now, basically, you have a really high pressure air at a really cold or medium cold temperature. Now that goes through the expansion device, which is the turbine here. Once that happens, now you have really low temperature and low pressure. Typically, you may be as cold as 1 degree C or 5 degrees C, okay, 1 to 5 degrees C here. And the water starts condensing, and you have to separate that water through the water separation device here. And once that's done, you basically are sent to a mixing chamber where you mix with a little bit of hot air from uh, the the jet bleed, so that you can raise this temperature from 501 degrees to around 20 degrees C and atmospheric pressure, right? And then you feed that to the cabin. Um, it's also mixed with existing cabin air, a certain percentage of existing cabin air, um, and some of it, some of the conditioned, some of the exit cabin air is basically thrown away outside the aircraft. Okay, the remaining one is mixed with the incoming cold air. Now, if you consider all these things happening, then the cycle is not exactly the Brayton cycle. Okay, you don't have a clean cycle like this. It's not one compression process. How many times do we have to compress? So imagine the state one is ambient, okay, outside. Air is outside the plane. And one to two, it's basically um, going, it's basically slowing down, okay? It's moving and coming to a stagnation point. Okay, stagnation point at the inlet of the engine and stagnation point at the ram air here. Okay, so pressure increases when airflow suddenly stops and hits the aircraft in a static location. And from that ram air point two, the jet raises the compressor jet raises the pressure to 2 to 3. And from 3, it is cooled down by the primary heat exchanger. This is the primary heat exchanger. So 3 to 4, okay, it gets cooled down. And then it gets um, compressed again with the secondary compressor, With the primary compressor is on the jet, the secondary compressor is in the pack. And this is what I mean by the secondary compressor. Okay, so here it's pressurized again from 4 to 5, right? Pressurized again. And then it goes to another heat exchanger where it's cooled down, the secondary heat exchanger, before it goes to the turbine. And in the turbine, it goes and cools down to really low temperature of 7. Now, this air is mixed with um, high temperature, high pressure air to get the right pressure and temperature. So the cycle have multiple compression processes. One is just because of the air that's flowing outside the aircraft stops at the intake of the aircraft. There is a ram compression, then compression in the engine, then compression in the secondary compressor. So three compression processes and one expansion process in the turbine. Okay, so it's a little bit more complicated than the basic reverse Brayton cycle. All right, so that gives you some idea of aircraft refrigeration system. And why do we use this system as opposed to a vapor compression cycle? This system is much less efficient than a vapor compression cycle. Um, why do we still use it? Well, primarily because you can combine pressurization and air conditioning into one operation. Okay, so you definitely want to give oxygen-rich air to people at the right pressures when they are traveling in an airplane. So you do need to bring in outside air to replenish oxygen. However, you want to pressurize it such that the oxygen is at the right levels, right? So even though the oxygen outside is at 20%, the outside pressure is zero point 0.2 bars. So if you don't pressurize it and bring zero point 0.2 bars of air into the cabin, it will feel like you're taking in less oxygen in each of your breath. So you do need pressurization and you do need outside oxygen and you also need air conditioning. So an air refrigeration cycle achieves all this, which the vapor compression cycle will not be able to do. Okay. Air is cheap compared to refrigerant, air is safe, and air is non-toxic and non-flammable. Uh, Depending on the type of refrigerant used, a lot of these things may not be possible. Okay. If you use a non-toxic refrigerant, you may be using a flammable refrigerant, which will create safety issues. Okay. If air leaks from the duct anywhere here in the cabinet, it's not a problem. It's actually air, so it's not toxic. And cold air can be directly exposed to people, um, and it could be directly conditioning the air in the cabinet. You don't need a secondary or you don't need an additional heat exchanger for that purpose, right? If we are using something else instead of air, we'll need a heat exchanger in this section, okay? Because we cannot expose people to that particular chemical. So instead, we'll expose a heat exchanger, which then cools the air in the cabinet. So we can reduce that heat exchanger, the need for that heat exchanger. Um, the aircraft engine already does majority of the compression process, so we don't need a large compressor. So that also saves weight. So we don't need additional large heat exchangers and additional compressors, so we save almost 50% weight of an equivalent vapor compression system. Um, and design of the system is overall much simpler because of the low pressures that are seen in the system. Even though the pressures you saw here were almost 200 kilopascals or more, that's still not significantly high compared to what you will see in a vapor compression system. Again, the last portion is again related to the simplicity of the system, that the number of maintenance required is also much less. All right, so that concludes this lecture on gas refrigeration cycle. Um, we had looked at primarily aircraft air conditioning cycle and not the cryogenic. Um, Aircraft air conditioning cycle is the most commonly used one and also the more simpler one between the two cycles. Um, the cryogenic cycle is beyond the scope of this particular lecture. All right, thank you.